Alrighty, let's get started. Now, so just so everybody's aware about the schedule, you all have present for me due today. Homework number 2. Today, I assigned homework number 3. Homework number 2 was the analysis of tension members. Homework number 3 is the design of tension members. It is due on Monday, February 17th. What happens on Wednesday, February 19th? We celebrate. We have our first exam. So it's going to cover 1, 2, and 3. Those first 3 homework assignments, primarily on tension members. I will tell you, of all the classes that I teach, this is probably the class where the exams are as modular as possible. In other words, we will test on tension members and then we move on. There's very little bleed over from one exam to another. I know for many of you having for classes, I say, well, it's not my intention that they be comprehensive. Well, it's pretty much not the case here. Just because of the mechanics are so different. When you have a piece of steel and you apply tension, it just behaves differently than if you take it and put compression on it, because steel likes to buckle and then the equations and the methods go out the door. It's completely different. So what we're going to do today is we're going to take a couple minutes and just finish that example that we started last time. We came really close to finishing it. We didn't quite get there, so it's only going to take a couple minutes, and then we're going to talk about this third limit state that we said, oh, we'll talk about that later. Well, now we're going to talk about it. This concept of a failure mode called block shear. Now, block shear is a little unique. The equation is very, very complicated, and I will tell you, you don't really design for block shear. What you would do is, in a design problem, you do what we did in the last example, like design according to yielding and fracture. Block shear would be something you just check later. And the reason why is you're going to see the equation is very, very complicated. There's no way to just solve for the area. It's a bit messy, so you just have to go through it. But let's just go back to the example that we were looking at. This is the example that we were doing. We had a W12 section that we were designing. It's 30 foot long. It has a dead load of 130 kips and a live load of 110 kips. The 110 kips was already reduced. So it's a W12 by something. We didn't know what that was at the beginning, and we selected a section. So sometimes I use the word select in lieu of design, but when I say select the section, that's what I mean. We're designing a W12. 8992 steel, 7/8 inch diameter bolts. And so here was the problem. We said, all right, first thing we did was factor the load. So we did 1.4 dead and 1.2 dead plus 1.6 live. 1.4 dead only governs when you have a lot of dead load. And that, to be clear, that can happen. Like if you're designing like a Golden Gate Bridge, that structure is so heavy that there are limit states where I can almost guarantee you the dead load governs. Like it's one of those bridges where if it can hold itself up, it can hold the traffic up. That's not the issue. But in most common instances, 1.2 dead plus 1.6 live is going to be the one that governs. And so we got 332 kips, and we had A992 steel, so the FY is 50, the FU is 65. And then it got into design mode. So our design expressions, basically what we're trying to do is solve for properties that we can look in the manual and find a shape that has those values. So we were trying to find a shape that had at least a gross area of 9.08 square inches and at least a radius of gyration of 1.2 inches. Now, the only thing I'll say is that, remember, when you're talking about the radius of gyration, make sure you're looking up the right one. You know, like for a W shape, it's RY. For an angle, it's RZ. For a T shape, it might be RX. So just make sure that you're using the right one. And so what we did is we picked one, and we ended up coming up with a W12 by 35, but that's a trial shape. We don't know whether or not that's the right answer because there's a whole bunch of assumptions that we made when we did this to get to this answer. So we have to go back and check it. So we look up all the properties, and then we just do a full-blown analysis start to finish. So we did that pretty quickly because we've done that a couple times. Between what you did on this and what we did in class, I think we've analyzed the W section enough times. So the net area is 7/8 inch diameter bolt, so a 1 inch diameter hole. Gross area, we took 4 bolt holes off that. I got a net area of about 8.22 square inches. Our U value is 0.85 because we went off of K7, and we got that our gross section yielding and net section fracture worked. And remind me, we had, so let's see, actually let me do one other thing to finish this example out. So slenderness, we had done this, is L over R. Now how long was this member again?
30 feet.
30 feet. So remember, when you're doing a slenderness count, don't use 30 feet. Use 360 inches. Divided by R, what was R?
1.2.
No, was that? No. This is a great point. What is R? What are we, now hold on, now let's talk about this. What R value do I use right here? And what am I doing? Am I designing or am I checking the section I have? I'm looking at a W12 by 35. What's the R value for a W12 by 35?
1.54.
That's the one you use, because what I'm doing is, this is my section. What is the L over R for this section? What is the L over R for this section? If I put in 1.2, I would get 300. That wouldn't tell me anything. I know what the slenderness limit is. I need to know what the actual slenderness is.
233.77.
233.77. So here's sort of like my design summary. Our BPN was 340.6 kips. Our PU, the design load, what we were putting on the section, was 332 kips. So what did the efficiency come out to be? It was efficiency
97.48.
is PU over BPN, which is 97.5%. Is that right? Okay. Whenever this value is 90% or greater, you're good. Okay. Let's make sure we're looking at strategy. I want everybody to turn to the W12 by 35 section in the manual. So the table 1-1. I want everybody to find that shape, because I want to make sure we're all speaking the same language. So I'm on page 1-26. I want to make sure that we're all clear on what we would do given these instances. Let's say that the efficiency was 73% instead of this 97. Let's say it was 73. What would you do? Now, first off, let's ignore the manual. If your efficiency is 73%, what can you tell me about the member? Is it over-designed, under-designed? Tell me, what does that mean? It's too strong, it's over-designed, right? Where the member's too beefy. It doesn't need to supply that much load, okay? So if the member is, or if the efficiency is 73%, what would you do? We've been analyzing a W12 by 35. I'm asking you, what would you do?
Try the next one.
And the next one is what?
The W12 by 30.
W12 by 30. So if your efficiency is low, go to the next one. And the next one is a W12 by 30. And do all of this again, okay? And what if your efficiency comes out to like 85%? Do it again. Go to the W12 by 26. Once you get an efficiency that's like 90% or greater, you're probably good, okay? I'm not going to make you go, like if you're ever on an exam and you get a 91% efficiency, I'm not going to make you go back and check the next one. You're good, okay? Sound good? Now, what if the efficiency was 105%? What would that mean?
You need to make it thicker.
It's not enough. It's not beefy enough. You're exactly right. So I have a W12 by 35. If my efficiency was over 100, remember, it's like the Price is Right. As close to 100% without going over. If I go over, I need to analyze the W12 by 40. So I take the W12 by 40, I do the analysis again, okay? So that's what I mean by iteration, okay? We didn't have to iterate this because our first choice, we had an efficiency of 97%. That's great. But if we ever encounter a situation where the efficiency is too high or too low, we have to do the analysis again. That's iteration, okay? I'm going to let me say this. I don't think it's healthy for you and on a homework or an exam to have to iterate like 6 times. You showed me you could do the analysis once. I get that you know how to do it. Everything past that is just hitting buttons on the calculator and wasting time, okay? But there is a possibility that you do have to iterate once, or you do the math and you have to do it again. That is real life design. I mean, that's just how it is, okay? There's only a discrete number of shapes in here, and so some of them are going to be more economical than others, okay? So that's just, it is what it is. Another final point, I do like to have a design summary at the end of the problems. The reason why is because you're making a lot of assumption and making a lot of guesses. I think it's healthy for you at the end of the problem to state everything that you know. What do I know about this section? Its capacity is 340.6, the load is 332. That means it's a safe design and it's an efficient design. I also know that L over R is 233.8. That's good as well because it's less than 300. So what is the answer to this problem? The answer is use a W12 by 35. That's the answer. The problem said we need to pick a shape that can resist these loads. That's the answer. Any questions? Yes, sir.
So, on the basis of a design perspective, we got this one beam to hold these loads.
Yeah.
So would we use that same beam for the whole floor area?
Well, okay. All right, so I've probably been a little defensive. I probably have thrown the word beam around more than I should. Beam would imply that we're bending something. We're not. So we are yanking something in tension. So if you want an example that relates, let's say, to a structure that we can all understand, what we're looking at essentially, imagine that we're looking at a truss. All right? Remember when we did truss analysis, what would happen? We would get some members experiencing compression, we would get some members experiencing tension, right? And so let's say I did a truss analysis and this member right here had a load of 332 kips in tension. If that member had a load of 332 kips in tension, use a W12 by 35 for this member. Maybe this member only has 150 kips. I probably wouldn't use a W12 by 35 on this member. Maybe this one's a W12 by 35 and this one's a W12 by 20 or something. I don't know. So the point I'm making is that because we're yanking on it, see, tension members tend to be used as either braces or tension elements in trusses. As a result, they don't really tend to get repeated as much, but for beams, that's a different story. Beams, especially internal beams supporting floors and buildings, if your building is quite regular, you can design one beam and repeat it everywhere that you have the same length and the same tributary area and the same loading. But with tension members, they usually are a tad more unique. You're probably going to be having unique braces for given stories. Like for instance, if you have a 6-story building and you have a brace on each floor, there's a good chance there are different braces on each floor. Does that make sense?
Yeah, so for like bridges and stuff, do you use the same beam at all, or do you have to analyze each member?
That's a great question, and it depends on the bridge. So, y'all hear news about what happened on 64?
Yeah, that's the bridge I used to cross over.
All right, so let's talk about that bridge, because that bridge is not simple. That is a complex structure, okay? There's a couple things about that structure to keep in mind. Okay, so first off, it's a truss, right? So if you look at the truss members, they're going to be different. They're not all going to be the same, okay? And it's because, I mean, that is a major structure, okay? And so as a result, each of those members are going to be tailored to their given load demand, okay? Now, that bridge is entirely different than a regular old everyday overpass, okay? Like a regular old everyday overpass might look something like this, okay? So here's the deck. That's your barrier. That's your truck. you're not getting any better at it. Okay, so don't criticize my artwork. I'll put some into that. Okay, here's the bridge. Okay, now this bridge is supported by a series of I-beams, right? In a structure like this, yeah, the I-beams, they're probably the same. You know, they probably are, or very, very similar. Now, even that can get a little funky if you're talking about, let's say, curved bridges, because when you have a curved bridge, that gets a little weird, because each beam has a different length and has a different, you know, that gets a little weird. And so your beams exterior to the curve might be bigger than the ones interior. But for a regular old straight bridge, yeah, they're probably just all going to be the same. If anything, your exterior beams might be a tad bigger, but usually they're all the same. That's a great question. So it just depends on the complexity. And ultimately, the overall answer I would give you is that whatever's going to make safety, construction simplicity, and least dollar value and least construction time is what's going to win. So, for a bridge like this, probably just use the same beam across the board. For something like that Nitro St. Albans Bridge, because it's so complicated, yeah, each member is going to be designed uniquely to tailor that load.
So what are they gonna do? Are they just gonna pour concrete?
That's a good question. I don't know. They have a couple different options. It's exacerbated by two parameters. First off, it's Interstate 64, so there's some traffic going on that bridge. Also, it doesn't help that you have to pour concrete in February during this weather, so that's going to cause some challenges as well. I mean, what happened was the expansion joint failed. Okay, so let's talk about that. Okay, now let's go back to structural analysis. Remember this? Okay, so this I have a support that resists movement this way. This one allows movement this way, right? Now, let's get in the helicopter and look down on the bridge. So, you know, here's the road, right? And so here's, you know, the ground, here's the ground, and so there's the river, right? So there's, you know, traffic lanes that Dr. Bryson wanted me to put there, and so here's cars, so on and so forth, right? That is an ugly car. Okay, now what I want to do is I want to look at one of the beams under the bridge, okay? Now, if I look, let's say, at like this beam, okay, so here's the beam. Okay, here's the beam. Under the beam, there's probably like a little plate right here and a little plate right there, something kind of like that, because I got to have something to attach it to the abutment, right? Something that'll attach it to the ground. So like there's an abutment right here. There's an abutment right here. Okay. Now, what we typically do in bridges is we have one bearing that's called a fixed bearing and one that's called an expansion bearing, okay? So a simple way of thinking about that is we might use like circular holes here to bolt that down, but we might use like a slotted hole here. Do you remember me talking about slotted holes later or earlier? That's a slotted hole. Now, why do we do that? Well, what happens when you stick a balloon in the fridge? And what if you stuck a balloon over a fire? It expands. Things expand and contract under various temperature loads. Well, bridges do the same thing. And you would be surprised at how much stress you can generate through thermal expansion and contraction. It's nuts. Like if you were to restrain this and let it go through a typical temperature cycle just on a given day, the amount of stress that you would generate is insane. That abutment would just be gone. You have to let the bridge move. It's got to move, okay? So what happened was the expansion joint on this end, so you have this sort of buffer here between there and there, between the actual bridge and the road. Well, gunk gets in there, leaves and rocks and dirt and all this crap gets in there, and that joint wasn't behaving the way it was supposed to. You get that expansion and concrete cracks. That's what happened. How they fix it? There's a couple ways. They probably need to actually repair the joint itself. They're probably going to have to pour some concrete in to patch that, to patch where, you know, the concrete failed. Right now, the pro is trying to figure out how to do it as fast as possible. So, can you fix it structurally? Yeah, you can fix it structurally. It's usually pretty easy. The challenge is the traffic. That and getting all your concrete to behave in February weather and things like that. So that's going to be the challenge. So I guarantee you there's a lot of phone calls going on right now about it.
So was it from the concrete deck that failed, or was it like the stress in the beams of like?
The concrete deck is what, I mean, the actual driving surface you can see right there.
Yeah, that's on the picture. I just wasn't sure if it was.
So it expanded too much?
Well, it wanted to, and it's not that it expanded too much, it's that it wanted to expand and it couldn't. That's what happened. So I'm telling you, thermal stresses, they are insane. Like, you would be surprised, like if you had a bridge that was restrained and you put it through, you know, let's say a 90-degree weather day during the day to maybe 60 degrees at night, just that temperature change, it's a lot of stress. It really is. Thermal expansion is not something to mess around with. So. Nowadays, when you build a new bridge, the idea is to cast what's called an integral abutment. So you have your beam, and so when you pour your concrete, all of this concrete is all like, it's all one pour. So you're trying to eliminate that actual separation. It's called an integral abutment. And they do that to eliminate that joint because expansion joints suck. They always fail. So you have to clean them out. You have to maintain them very regularly, and it sucks. Don't do it. Integral abutments all the way. I went off on my tangent a bit there, but
They've only been doing that for a few years now, haven't they?
integral abutments? Well, you can only, I mean, you have to use it where it's appropriate. They are starting to catch on with the construction, the bridge construction industry. You are correct that it is a newer, you know, a newer innovation. We're probably going to have different maintenance challenges with integral abutments down the line because they're so new. It's like you don't have a large population of 60-year-old bridges with integral abutments. Go, okay, now we know what's going to happen to them. So I'm sure there will be maintenance challenges down the line, but right now, are they better than regular old expansion joints? Yes. Yes. So yeah. Are there any other questions about what happened there? I mean, this is just from what I've read and what I've seen, you know, in the field, and I talk about this stuff all day.
How often do like those bridges have to get inspected?
2 years.
Every 2 years?
At least, yeah.
And the that bridge is a little different. That bridge would be classified as what's called a fracture critical bridge. So, anybody remember what happened on December 15th, 1967? Or no, 1967. Silver Bridge collapsed. When the Silver Bridge collapsed, the reason it collapsed is because a single load-carrying member failed and it caused the collapse of the entire structure. That phenomenon is what's called fracture criticality, the idea that if one member pops, the whole thing comes down. Now, you take the Nitro St. Albans Bridge, it's a truss, like it's a 3-truss. So trusses are considered fracture critical because you have a truss here and a truss here. If this truss fails, the whole thing's coming down, or at least it'll result in either total collapse or partial collapse. That is concerning. Because of that, those bridges require hands-on inspection. Their inspection requirements are far more stringent. So, but the truss wasn't that wasn't the issue. It was the deck. So, and let me say this: I without knowing all of the details about that failure, it seems like something like that probably isn't unique to that bridge. Like that stuff could happen on any bridge because bridges expand and contract, expansion joints are used, you get gunk in there, it doesn't expand, and concrete fails. I don't think that was unique to that bridge. If a failure that was unique to that bridge happened, it'd be far worse. So.
Isn't it odd that it failed on like kind of a colder day when it was like 70 degrees the other day? Like you would think on a colder day.
Well, it didn't fail on a colder day.
Well, it was yesterday, wasn't it?
Well, yeah, yesterday wasn't this.
Well, yeah, but like a couple days ago, it was like 70 degrees.
Well, you could think it. You could argue that maybe, I don't know, like you think it would expand and it didn't. It's probably more just because of stuff building up and just the joint not performing the way that it should. Expansion joints are always maintenance problems, so they really are. I joke, and again, I joke in concrete design that there's only 2 types of concrete in this world, and that's wet and cracked, but that really isn't a joke when you talk about maintenance, because yeah, it's challenging.
So if expansion joints have been bad, then why didn't they like come up with a new ideas sooner before using expansion joints?
You got to understand that the market changes and has changed in the bridge market for the past decade. See, I'll give you an example. You can tell an older steel bridge by a newer steel bridge by just looking at it, even if their conditions are the same, by the way it's fabricated. If you see a steel bridge that is that has a lot of stiffeners, like a lot of plates going up and down, and bolts and rivets all over the place, guarantee you that's an older bridge. Newer steel bridges are boring in their fabrication. It's just like an I-beam, just plate, web plate, and that's it. See, back in the day, back in the 50s, 60s, 70s, we were in an environment where material was expensive, but labor was cheap, right? So the idea was, I'm going to shave every single pound of steel that I can off that bridge in order to reduce the cost. If I have to throw a few more labor hours at it, so what? You know, that's not a problem. So at the time, it's like, we're going to produce the cheapest material solution possible, and if we have to go back and fix it, who cares? That's cheap, right? Now it's a little different, right? Now we're in a world where the labor is very expensive. The material's cheap. I'll make the bridge 5-10% heavier if it means I don't have to go back and fix it. But then you get into this issue. Now we got a bunch of 40, 50-year-old bridges that we got to go and fix, right? So things changed. So that's like my simplest answer. Nowadays, that's what I said, like with integral abutments. Like nowadays, we're using systems to try and head off those problems in the future. See, because the market changed, the solutions that we are now using have changed as a result. We're trying to avoid that stuff in the future. So, like an integral abutment, you cast the deck and the abutment, integrally, you don't have that joint, so it's something that won't fail in the future. That's sort of the idea. So.
You think they'll ever take that expansion joint out and redo it?
They're going to have to do something. I guarantee their solution right now is we just got to get something serviceable. That's what they're doing right now. They're like, okay, we need to open traffic. What can we do to open traffic? And that's what they're going to do. If they have to go back 6 months, a year from now to do something for real, that's a very possible decision process that they're going. And there's nothing wrong with that, as long as they're producing a solution that's safe, that can support traffic. They're not going to say, well, it's a little flimsy, but we'll let people drive over 64. They're not going to do that. So they'll hold traffic up. So yeah, this is good stuff. I like this.
Are they planning on expanding that bridge, like making it wider to make the I-64 bigger?
I don't know. Now, it is common practice when you're designing bridges on large volume roads that you might have two 12-foot lanes and two 8-foot shoulders, like really wide shoulders. And the reason that they do that is because if they decide to go 3 lanes, they've got the room to do that. I don't know. I'd have to actually go drive down that bridge to see if they have the room to even put another lane on that bridge, and I don't think they do. So the only way to do that is to build a new bridge, and that's a thing. That's going to be an effort.
Because I know they're trying to expand I-64 from Huntington to Barboursville area. I'm not sure if they're going to it's already kind of expanded in Tays Valley area, each side has 3 lanes.
Well, the bridges, like the one near the Target, that exit near the Target and the Home Depot, that is a much more typical bridge to replace than that Nitro, St. Albans Bridge. That thing is a unique snowflake, and so it's a large, complex structure, and so that's not something you just decide one afternoon. You've got to plan that out. There's a lot of money. There's some complex engineering that goes into how do we widen that bridge. That's not something you just do in an afternoon. I don't know. Maybe. To me, my complaint is more about the exit deal right there.
Yeah.
That sucks.
Yeah, I've noticed that. I've seen that all the time.
As soon as I pass that, if I'm not in the left lane, if I'm headed towards Charleston, I'm not in the left lane, I'm nervous.
Exactly. I get that way every single time. I've actually been pushed over twice in that area.
Yeah, I hate it, yeah. So I get to the point now where if I'm like in Taze Valley, I'll get in the left lane just because I don't want to have to deal with that when I get there.
Yeah.
Any other questions? This is good stuff. I like this. We got the time too. All right, let's talk about block shear. Before I do though, I'm going to go off on another little tangent, and I'm going to talk about a failure criterion called the von Mises failure criterion. Now, how many of you have already had soils? Already had it? Geotech. Okay. Did y'all discuss more Coulomb failure criteria in there? How many of you are in it now? Okay. You probably haven't discussed it yet. You will. Okay. Let me explain what a failure criteria is and why the heck I'm even bringing this stuff up. Okay. Now, a failure criteria is either an equation or a model that we use to look at a given state of stress and ask ourselves, has this element failed or not? Okay? Now, if I have a metal, right, a piece of metal, a very simple failure criteria would be a yielding criteria. I take it, I yank on it, when the stress hits the yield stress, it's fatal. That's simple, right? Now, that's simple because I'm taking the member and I'm loading it uniaxially and just yanking on it in one direction, and so once that stress hits the yield stress, that's it. That's simple mathematically. What gets complicated is the fact that materials are not always simple, okay? Sometimes they behave in a very complex fashion. You will use a failure criterion in soil mechanics, I guarantee it, called the Moore-Coulomb failure criterion. And so what you do is you relate the normal stress that a section of soil is experiencing, the shear stress that it's seeing, along with two properties related to that soil, its cohesion and its angle of internal friction. So, for instance, and this will become an analytical problem for you in soil mechanics. So, if you ever have a sandy soils are cohesionless, so you'll take the C value to be 0 and stuff like that. You will do this in soil mechanics. You probably have it now. You will, I promise. And so what you do is you plot that. It's very similar to a Moore's circle plot that you did in Engineering 216. And so you'll say, okay, based on this state of stress, the soil has either failed or not. Okay? Now this failure criterion is appropriate for soils. Soils they can behave like brittle material. Sometimes this type of phenomenon is used for concrete because it's a brittle material. This failure phenomenon is not what we would use for metals, for ductile materials like steel. For steel, the material phenomenon that we use is the von Mises criterion. Now, like I said, a simple yield criterion would be if I'm taking the steel and I'm yanking on it, and once the stress hits Fy, that's the failure. That's simple. That's easy. The problem is that steel, it's not as simple as just yanking on it. We could be yanking on it, twisting it, pulling it, bop it, twist it, pull it. Remember that? You could take this section of steel and heat it up, twist it, and shear it, and yank on it, and do all sorts of different things on it. You could generate stresses and shears in 3 different directions. So how do you know whether or not this is yielded? It's not as simple as whether the stress hits Fy because the stress is going all over the place. Okay? So what we have to do is we have to develop a model that says, okay, based on this stress state, it's either yielded or not. Now, don't worry, I'm not going to make you use the von Mises criterion, but this is the von Mises criterion. It is the failure criterion that we use for ductile materials. I know it looks complicated, but it's actually in 3 dimensions. It's probably the simplest yielding criterion that we developed. Steel, from a materials perspective, steel behaves pretty simply. It's a very simple material. It's not like concrete, where concrete has different behavior in compression than it does in tension and things like that. It's different. Steel is simple. Okay, so what you do is you plug in your normal stresses and your shear stresses, and then compare that against your yield stress and see whether or not it yields. The reason why I'm telling you this is because I'm more interested right now in shear. What happens if I take a piece of steel and shear it. See, if I take a piece of steel and I yank on it, it yields when the stress hits Fy. But what about when I shear it? Does it yield when the shear stress hits Fy? The answer is no. It actually yields at a far lower stress. If you take this equation and set all the stresses equal to 0, but one of the shear stresses, like, in other words, take an element and put it under shear. That's it. Shear it and see when it yields. Plug and chug, and you find that its maximum shear stress before it yields is not the yield stress. It's about 57% or 58% of the yield stress. So think about it like this. If I'm taking a piece of A992 steel and I yank on it, axially loading it in tension, it will yield at 50 KSI. But shear it, and it's not 50 KSI, it's like 57.7% of KSI. So shear capacity is actually lower than the normal capacity. Does that make sense? Okay. Now this number 57.7, I just want you to keep that in the back of your head. So block shear. What's going on with block shear? Block shear is a really, really unique phenomenon. It's actually kind of found by accident. They were doing some tests in the lab in Canada, and this happened, and they went to their supervisor and said, "Look at this." And they're like, "Do that again." And so they did it again, and sure enough, it happened again. They're like, "Oh, I guess that's a thing." So we kind of need to figure it out. And so what block shear is a failure path that consists of tensile failure along one path and shear failure along another. I have this video that I pulled up a while back. I'm actually going to pull that back up because I think it's a whole lot more descriptive than the picture. Give me a sec. Okay, so here we have an angle and we're loading it in tension. Okay, so it's a tension member. We're yanking on it, pulling it away from the connection. Okay. Now what happens is we get sort of a mixed failure phenomenon. Okay. Here, so let me draw this on the board here. So here's my angle. So this is the leg sticking out, and here's the angle, and I've got that bolt and that bolt. What's happening is you're getting a mixed failure phenomenon. I'm yanking on it, and so this sort of chunk right there, that sort of rips out. Well, from a mechanics perspective, if I'm yanking on it, this right here is experiencing tension, okay? But this is experiencing shear, okay? Because you're yanking on it this way, and so it's, this is wanting to sit still, the angle's wanting to move, so that path is seeing shear. Does that make sense? So it's not as simple as just an area times Fy. There's a lot more going on, okay? So, go back to slide 30. And so what happens is you have a combined failure path where you can have shear yielding or shear fracture along one path and tensile fracture along another path. And there's some other images from the test at Georgia Tech and the test at WVU where you can see the result of that type of failure. Now the equation for block shear looks a little nuts, okay? You're like, whoa, it was just like FYAG and now there's all this crap going on. What's the deal here? Okay, so before this equation scares the hell out of you, it's really not that bad. First off, let me show you a couple of things. Do you remember that up until now we've been operating in Chapter D? Because Chapter D is the design of members for tension. Well, if you look here, this is in Chapter J, okay? Chapter J is the chapter on connections, okay? I'm going to tell you that we're going to be spending a good bit of time in Chapter J for the foreseeable future. So this is sort of our first dip into it. This is technically kind of a connection check, so well, we'll be looking at that. Now, the phi value is 0.75, so that's easy. All right. Now, what about everything else? Now, there's a lot of, to be honest, there's a lot of crap going on here in this equation, but it's really not that bad. Okay, first off, there's Fy's and Fu's. Those are simple. But what about the areas? Well, if you look at the terms like ANV, ANT, AGV, gross area and shear, net area and shear, gross area and tension, net area and tension. So it looks complicated, but it's just a bunch of areas. It really is. So it's not like it's anything very complicated. The one thing that's really new, I would say, is the block shear reduction coefficient, and that's going to be 1 for like all the cases that we look at. So it's really one of those things where once you start going through the example, it's really easy. Now, what probably does look a little weird is what is the deal going on with this? Like you got Rn equals this pile of junk less than or equal to another pile of junk. That is just the specifications way of saying that it is the minimum of those two expressions, okay? So whenever you have that in the spec, and we will have a number of instances where that pops up, whenever you see an equation equals a quantity less than or equal to another quantity, that's just the equation's way, or the spec's way of saying it's the minimum of those two expressions. Now, if you look at these two rows, you have this plus this, this plus this. The second term is the same. So I can pull that out, and I can also factor out the 0.6. Okay? So I can take this and I can make it a whole lot simpler and a whole lot easier to deal with. Now I want to look at that box, and I want to show you what I got going on in that box. I've got that the nominal capacity equals, and there's really two terms. There's a pile of junk plus another pile of junk. The first term relates to everything going on in tension, and the second term relates to everything going on in shear, right? Because if you look at the first term, it's UBS FUANT. It's the tensile component. Everything over on the right is FYAGV, FUANV. Those are the components related to shear. See that 0.6? Remember that yielding criterion? It was like 57.7? Spec said, oh, what the hell, just round up to 0.6. Every time that we have a component that has shear related to it, there's a 0.6 in there. Okay, when we look at bolt bearing, tear out calculations, or we look at the capacity, there's a 0.6 in there. When we look at shear capacity of beams, there's a 0.6 in there. This 0.6 is going to pop up a lot. That 0.6 comes from that failure criterion for elements in shear. Okay, so that's just something to keep in mind. The only thing that's unique is UBS. In most cases, UBS is just going to be 1. UBS is kind of like a shear lag factor for block shear. It just accounts for non-uniform stresses. The only time that you ever take UBS to be 0.5 is when you have multiple rows on what's called a coped beam. So what a coped beam is so you know how when we have floor systems, we have beams framing into girders and so on and so forth. So how do you connect? Oh goodness, how do you connect? So I have, let's say, here's a girder, and I have a floor beam that's coming into it. How do I connect that floor beam? So this is the floor beam coming into it with the flanges sticking out. How do I connect that so that the floor sits level? Well, what I do is I say, let's cut a chunk of that out so that it can come in and sit flat, and so I can bolt those together. That's called a coped section, when you cut that part out so that when you connect that to a girder, the floor remains flat. And if you ever have multiple rows on a coped section, you take UBS to 0.5. Everywhere else, UBS is 1. So yeah. Sound good? All right. One final thing, and we are running a little short on time, so I'm not going to delve into the example today, but kind of like with net area, there's a possibility that multiple potential failure paths could happen with block shear. For instance, you could rip out this chunk in the middle. You could also have a block shear path where you rip out this and that. So This has like 2 shear paths, 1 tensile path. This has 1 shear path and 1 tensile path, but the tensile path is longer. So there's actually 2 different ways that section could fail. Now, when we start doing the math, we'll go back to this, and you'll see that for this problem, that's the one that's going to govern. I can go ahead and tell you. But once we do the math, it'll be a little easier to talk about that. Now, I'm sure some of you might ask, well, wait a minute, what about all of this? What about all this chunk? Well, that's just net section fracture, right? Because what is net section fracture? When it just fails along that net section. So could this whole chunk rip out right here? Yeah, that's just 0.75 FUANU. That's just the whole net area because there's no shear path. So yeah. Sound good? All right. Okay. We're going to start this example on Monday, but I actually want to show you the homework assignment. So this is the example on Monday, but I want to show you your homework assignment because I got finished making that right before class. So here's your assignment, and you've got 3 problems. So for this problem, so you have problem number 1, I want you to design a tension member. It's going to be much like the example that we did in class, but it's going to be a W8. So I want you to design this tension member. The second thing I want you to do is I want you to look at this angle and compute the block shear capacity. That'll become a whole lot easier after Monday. But the third problem, I want you to design this channel. The difference between problem 1 and problem 3, problem 1, I want you to ignore block shear. Problem 3, I want you to consider it. So with problem 3, you got to do it all. You got to do block shear, you got to do yielding fracture, all of that. Our last topic on the exam, I will go ahead and tell you, is threaded rods. What we're going to talk about after block shear and in between is an event called the High Regency Walkway Collapse. I'm curious, how many of you have heard of that?
Was that the Florida?
In Kansas City. Are you talking about the FIU bridge? No, this was a long time ago. This is in the 80s, okay? To date, this structural failure is the worst failure in design, under its design load in U.S. history. This is different than 9/11 or the Oklahoma City bombing, where the buildings experienced what we in structural engineering call extreme events. This was not the day-to-day performance of the building. Like when the Oklahoma City bombing happened, there was broken glass reported in buildings up to a mile away. The bomb that went off was parked next to one of the columns, and the explosive force was so drastic it shattered the column. Literally shattered a steel column. Yeah, that look right there. There's no way you're designing a building for that. See, nowadays in structural engineering, when it comes to blast resistance, it's not about design more than it is threat deterrence. Why do you think the Army Corps has those posts in front of the building? And so you can't park a truck up to the building with the bomb in it. That's why they're there. Okay, so that's why we do that now. But this was a little different. There was an elevated walkway in this building, and it was experiencing its design load. This was what it was designed for, and the walkway collapsed, and over 100 people died. And this is the worst structural failure in U.S. history under that event, and it all revolved around the detail associated with a threaded rod. So we're going to do a threaded rod design problem in here, kind of similar to that, but that'll be our last topic before we go into bolted connections for material on exam 2. So we'll talk about that on Monday and whatnot, but that's all I've got for you all. Again, if you haven't turned in your homework, I need that. If you're in concrete, you didn't get your homework, I still have a couple over here left over. And that's all I got. Y'all have